Hello, ladies and gentlemen. Now I will start my report on mathematics. This is one of the reports which I plan to make in Belgrade in this month. It would be at 13th of December. Today is 7th of December 2025. The Kyiv time is almost 11:15 p.m. And now we'll start the first of three reports that I plan to make. So we can to start. Now I would like to make the demonstration of my laptop. Please some wait now. So this is my talk with Victoria Desyatka, who is my postgraduate student. She has some problems with English report, and it was the surprise for me because it is very easy. It is very easy to make the mathematical reports. There are no any difficulties to make. So I would like to give some example of such a report now for the goal that my students to see that it is not difficult. It is very, very easy. So please some wait. I would like to make the full screen. Okay, so the report is devoted to the problem of isolated singularities in Riemannian manifolds. This is a more strong situation, more difficult case with respect to the Euclidean spaces. We have with Victoria some results on this topic. In particular, we have the most important results in the Euclidean space, but this result was published in the Ukrainian Mathematical Journal in 2024, concerns the Riemannian manifolds. Recall that Riemannian manifold, or an n-dimensional topological manifold, is a Hausdorff topological space with a countable base in which each point has a neighborhood homeomorphic to some open subset of Rn. So it is easy to see on the picture that we have some point P in some structure, say Hausdorff topological space. It is not important what is this. So we have the neighborhood U, which maps with the help of the mapping phi onto the unit ball or some open set in Rn. This is mapping phi is called a card on a manifold. More precisely, a card is a neighborhood with this mapping phi. So what is a manifold and what is the card? A manifold is a sum space which has a neighborhood homomorphically mapped to Rn. If P belongs to U, we have the corresponding points x1, etc., xn in Rn, and the corresponding numbers are called the local coordinates of the point P. A smooth manifold is a set Mn together with the corresponding family of cards, such the union of over alpha of all the U alpha gives the whole of Mn, where the corresponding transition maps are C infinitely smooth. So there is no picture here, but this text must be understood as following. So if we have one card and some another card, so they map our neighborhood U for some sets in Rn, so we may construct the transition mapping between these cards, and this mapping must be C infinity. What is this? This mapping has all derivatives of any order, and they are continuous. The next paragraph. We next recall that a Riemannian metric on a smooth manifold Mn is a positive, definite, smooth, symmetric tensor field of type 0, 2. In particular, the components of a Riemannian metric, G, K, L, in different local coordinates, U, X, and V, Y, are related to each other according to the tensor rule. What is the sense of this paragraph? So if we have two local coordinates, we may construct the transition mapping, C above. But this transition mapping, these coordinates, must be connected by the corresponding rule. This rule is written here. Once more, if we have two local coordinates x and y, so y equals to y from x, then the matrix components Gij and Gij tilde and GKL must be connected by this rule. For simplicity, you may take some mapping in Rn and to calculate what is the rule which allows to calculate the derivatives of the image and preimage. So we observe that this is a mapping rule of a such type, must be. In the next formula 1, we define the length element and the element of volume on the Riemannian manifold. So the length of a smooth path gamma joining points M1 and M2 and the n-dimensional volume of a domain A in a Riemannian manifold are defined by the rule 1. So Gij as above and here as well is some system of matrices. Gij in X is some matrix n multiply n dimension. If we have local coordinate x from t, then the length of gamma where gamma is defined on the segment T1, T2, is defined by this formula. Similarly, the volume of the set A is defined by the formula in the right-hand side of the one. These formula are some difficult, but they have some sense. What is this? If we have two local coordinates, for example, x from t and y from t, then if we calculate L from gamma through y from t, the length is not changed. Similarly, the volume. So this quantity, it may be showed that this is an invariant under the change of variables x from t. If we have some another representation y from t, this quantity L from gamma is not changed under the change of variables. Similarly, the quantity in the right-hand side of 1 is not changed as well. So the matrix system GIG is called a tensor, and this is quantity, say, allows to define correctly the length and the volume on the manifold. Here we also have a picture. This is a path gamma on the manifold. This is a set A on the manifold. We made to translate under the mapping phi A or gamma onto the Rn space, and here we may calculate the length and the volume by the formula 1, because in Rn we know what is this, the integral of a such type and such type. So on the manifold, it is not defined the length and the volume by the definition. Only in the space Rn by the transition formulas 1. On the next page, we deal with the geodesic distance between points P1 and P2 on the Riemannian manifold. We define this distance by the smallest length of a smooth path joining P1 and P2. The length is defined as above, and the smallest length, the infimum of the length of such a path, is well defined. This distance between points P1 and P2 is called a geodesic distance. In the next page, we, as usually, define the ball centered at the point x0 of the radius r, the sphere, and the ring at the corresponding center and of corresponding radii, where dv and dv star are volume measures on Mn and Mn star, where Mn and Mn star are some manifolds. Generally speaking, different manifolds. Recall that the volume is defined as above in 1. Also, we define the distance between sets and the diameter of the set. Here we use the geodesic distance only. So the geodesic distance at the mapping, the manifold Mn is defined as D, and in the manifold Mn star is denoted by D star small. There is no D star small on this picture. Oh, there is D star small. At this page, we talk about normal neighborhoods. A normal neighborhood of a point is a neighborhood in which the distance between points equals to the Euclidean distance between the mapped points and the mapping phi. So let us to consider the definition. It is well known that any point P in a Riemannian manifold Mn has a neighborhood U, a normal neighborhood of P, and a corresponding coordinate mapping phi, such that the geodesic spheres centered at P and radius R lying in the neighborhood U are taken under the mapping phi to Euclidean spheres of the same radius, and the pencil of geodesic emanating from P is carried over to a pencil of radial segments. Some more easier explanation follow from this picture. So we have here the balls and the spheres on the manifold. We see that this ball and spheres correspondingly, respectively, map under mapping phi to the usual ball and usual sphere. Here is the definition of admissible function. This is a definition I am many time to give. So a path gamma is a given path, and a length of this path is defined as a supremum of these sums over all partitions of the segment AB by the points Ti. A Borel function ρ is called admissible for a family gamma big if the relation 4 holds for all locally rectifiable paths gamma small and gamma big. A modulus of gamma is defined by the formula 5. Gamma EFD is defined by the family, is defined as a family of continuous paths joining two sets E and F in a domain D. This definition, as above definition, is not changed in the Euclidean space and in the manifold. There are the same definitions, but in the Euclidean space, we write here the GM, where M is the Lebesgue measure. And in the manifold, we have V as a volume measure, which is defined in 1. So all these pictures, 1, 2, 3, 4, particularly 5 and 6, we only need these pictures only for this to define the measure V and the length L. All another definitions, all another notions, all another conceptions coincide with the Euclidean conceptions. So we, in fact, we will say about the objects some things as a Euclidean space, similarly to the manifolds, and in other direction also. So all other definitions coincide with the Euclidean definitions. here there is a definition of a mapping with inverse Politsky inequality. Let x naught in D and the number R naught bigger than 0 be such that the ball B lies with its closure in some normal neighborhood U of the point x naught. Denote by SI geodesic sphere centered at the point x naught and radii R1 and R2, given sets E and F in G in N. We denote by the triple gamma E of G the family of all paths joining E and F in G as above. If D is a domain in a Riemannian manifold and F is some mapping, Y naught is some point, and R1 and R2 are some numbers, then by gamma F, Y naught R1, R2, we denote the family of all paths, gamma small, in the domain D such that F from gamma join the spheres of the corresponding radii centered and the corresponding point Y naught in the ring A. Let Q be a Lebesgue measurable, be a measurable function, measurable with respect to measure of the volume in one. So measurable function with respect to the measure V star. So Q is defined in the mapped manifold, two manifold, Mn star, not Mn, but Mn star. We will say that F satisfies the inverse Politsky inequality if 6 holds for every function eta for which 7 holds. We see that the transformation under the mapping F satisfying the inverse Politsky inequality on this picture. Observe that there are many mappings of such type, especially quasi-regular mappings and mappings of the Sobolev class as well. For simplicity, we don't give this information in detail because you see on the picture here all need information, all required information here. Recall that a mapping F is open if it preserves open sets and is discrete if the prior image of any point have pairwise disjoint neighborhoods. Let D be a domain in X and D star let D star be a domain in Y. Everywhere below the closure A dashed and the boundary dA of the set A in Mn should be understood in the sense of the geodesic distance D in Mn. Let I be an open, half open, or closed interval of the real axis. Here we use some generalization of the notion of the Riemann sphere and of the Hordal metric in Rn. So let Mn dashed is defined as Mn with the union of the formal symbol infinity, and let H be a metric on Mn dashed. So we supposed here that this metric exists. So we don't say about the cases when this metric exists. Is another question, more difficult. Suppose that the manifold Mn is connected, then D is a metric on Mn. I will say that H satisfies the condition of weak sphericalization if Mn H dashed is a compact metric space and H and D generate the same topology on Mn. There is an example of them space with sphericalization. So the usual space Rn satisfies all these requirements. Why? Because we may to consider some points, x and y, and we see the projection of these points onto the Riemannian sphere in such a way as in the picture. We may to calculate that the distance between px and py is the segment. The length of this segment is calculated clearly, is maybe calculated, but I didn't give this formula on which is calculated, and it is not essentially in this picture, but there are formula that are very well. The reader, the participants may find this formula, for example, in the well-known book of Vyasela. I recommended this book to my postgraduate students, and not only for them. The main result is the following. Setting Qx naught from R as follows, we consider the following theorem. Let n bigger than 2, let D be a domain in N, let x naught in D, let A be in Mn star, A does not equal to B, and let F be a mapping which is defined in the punctured domain D without of a point x naught. And let F be a mapping which omits these points A and B mentioned above, be a known but discrete mapping satisfying the inverse Politsky inequality. This inequality 6. For every non-negative measurable function eta satisfying 7. Suppose that the manifold Mn star is connected and admits the condition of Wick's fertilization as this. Suppose that in addition that for each point y naught in the mapped domain C above, there exists R naught bigger than 0 such that this guy is finite for almost all R. Then F has a continuous open and discrete extension to D, where continuously of the mapping should be understood in the sense of the so-called Hordal metric. But this is not Hordal metric, it is abstract Hordal metric, which is defined as above. This result was published in Ukrainian Mathematical Journal last year. Thank you very much. It's over. So this report need some working onto the notions of the Riemannian manifolds. I think that the most difficult part is the part concerning Riemannian manifolds. These pages are more difficult for my students, I think, but there is some time to study these things. Another part of the report, starting from the definition of the modulus, etc., is respectively easy because there are things that we many times to discuss in our seminars, for example, and there are in our papers many times, many papers. So Thank you very much. It's over for now. Now is 23:12. Good luck, goodbye, and слава Україні!